Now we're looking into supervised model. So what's the main difference between supervised and unsupervised? I shared it a little bit, but it boils down to a very simple thing. In unsupervised, I do not have a target to compare my performance with, my model's performance with. But in supervised model, I have a target. So it might be a sales prediction. It might be default or not default. It might be who's going to go away, churn. It might be how much a person's gonna lend from us, borrow from us. It can be how, how regularly a customer is gonna come. So all these where we have that data and we're trying to fit a model which is the best model to predict that data. The beauty of supervised learning. So I was talking about the beauty of unsupervised learning, and I don't want to be biased towards one type of learning. I'm married to both. So in supervised learning, the beauty of supervised learning is that you get accuracy results. You can compare your model with real life data and identify which model is the most accurate one for your situation. This is something you can't do in unsupervised model. Unsupervised model is shooting in the dark, but playing around in the dark to figure out, okay, you're going to hit the target. Whereas in supervised model, you know the target. You hit it and you find out which throw was the most accurate one, which model worked the best. So the most widely used supervised model, and I'm sorry for the joke it's followed with, is regression. I know that, when you're doing stat classes, you were thinking like, okay, past, done with it, never going to look back at stats. But unfortunately, stat class is back at you. So, regression is one of the most used supervised model. There are some reasons behind it. The first reason is simplicity. So sorry about that. Most regressions, and the most commonly used is actually the one in the left, linear regression. Linear regression assumes that there is a straight line relationship or a linear relationship between two variables or multiple variables. And it tries to model that. The other beauty of regression is it's explainable. That is, when you fit the model to predict something using regression, the model can be explained to anyone. Say a regression model, say suppose I'm trying to find out how much advertisement causes sales. Say, I found out equation, which is like this, that sales is equal to 1,000 plus 50 into per advertisement. This basically tells me that if I don't show any advertisement, my sales will be 1,000. If I show a single advertisement, my sales is going to increase by 50. If I show two advertisements, the sales is going to increase by 100. So marginal increase of 50. This is very easy to explain to anyone. And if you try to understand that, not only just get a prediction, but get an understanding of what is happening with your data, then regression is the best way to go forward. And I put it quite strongly. Now, what are the problems with regression? It's not as accurate a model as it needs to be all the time. But then there are also concepts of quadratic regression, cubic regression, which are a little bit more complex than linear regression, but they are more accurate to fit many different really complex relationships in the data. So good, relationship is very good if your data is following a linear trend or a simple pattern, like a simple quadratic pattern, like a simple cubic pattern. Nothing like a data which is like this, and this, or very mixed pattern data. Not going to help with regression. So complex patterns, regression is not as suitable. The other thing is regression is good for large data sets, because the larger the data set, the more examples the model has to fit the best line of fit or the best curve of fit. So, and also regression is good if you are in a situation where not only the prediction is important for you, but also understanding that which factor leads the most impact to your target variable. Then regression becomes more important. Now, not suitable for complex patterns. The other thing not suitable is if you're trying to make a prediction which is outside the range. What do I mean? So let me give you an example. Suppose you're trying to fit a line between, trying to predict a person's spending, and say the data you have has a maximum spending of 10,000 taka. And maybe just keep it simple. You're trying to predict a person's spending based on the amount of discount provided in the type of products he buys. And say the discount data you have, the lowest discount given is 20%. Now, If you're trying to answer the question that would 40% discount lead to a sale of 25,000 taka? Unfortunately, regression is not really that good for it. If your data set has the highest spending of 10,000 and the lowest discount of 20%. So the data range, when you need to extrapolate beyond data range in any direction, regression models tend to not do good. So this is one word of warning. Use cases, there are many use cases of regression. There is demand forecasting, there is predicting people's potential spending, potential outcome of a discount, potential outcome of an ad campaign. Many things can benefit from a regression analysis. Moving on to the next part, binary regression. Binary regression means that instead of predicting a single number or single value, binary prediction is where we try to predict a yes or a no, a 0 or a 1. A simple example would be, we have discussed this in previous sessions as well. Would be credit modeling, because credit modeling is where we try to figure out whether someone's going to default or someone's not going to default. And that's where logistic regression, probit regression, so binary regression comes in handy. Again, regression is good if you also want to know which factors lead to the 0 outcome or which factors lead to the 1 outcome, which factors lead to a yes outcome or which factors lead to a no outcome, which factors lead to someone defaulting and someone not defaulting. But binary regression is limited to the fact that it can handle multiple outcomes like yes, no, maybe, or 0, 1, 2. It's called multinomial regression, but this becomes super complicated and super inaccurate as well. So if you have to predict multiple outcomes, multiple classes, like maybe you're trying to predict whether a person's going to stay or not stay, or maybe, or a person's going to be happy, not happy, or unhappy. So, or maybe a person's going to spend high spender, medium spender, or low spender. So multiple criteria like groupings come in, then binary regression is not very useful. So use cases, yeah, as I was discussing, customer going to default or not, or customer churn prediction. The next part is decision trees. So in the left-hand example, it's a best example in terms of the most common example of usage of decision trees. So this is actually the decision tree of Titanic, trying to predict who survived in Titanic. So it's a very simplified version. There is a much larger version of it. You can search the Titanic decision tree. It's quite popular. So here, the data is being asked this question, okay, if the person who is in concern, male or female. So if the sex is male or female, so if the sex is no, that is sex male is no, which means the sex is female, then survival rate has been, most of them have survived. 36% of the people have survived from the full data. And then there is, if the sex is male, then whether the age is greater than 9.5. The left hand is yes, the right hand is no. So if it's yes, and the age is greater than 9.5 and a male, then they have died. If no, then the next question is CBSP, which is number of siblings, greater than 2.5. So technically, if the number of siblings is greater than 2 or not. So if the number of siblings is greater than 2, then they have died. If the number of siblings is not greater than 2, then they have survived. Basically, the decision to save, put people from in the sinking Titanic to lifeboats was, first of all, ladies first, and the second was children. And among children, unfortunately, if it was a large family, then chances of your survival would be less, because one children for family or 1 or 2 children per family was able to be rescued. So decision trees come in handy when we don't have a nice linear relationship, when we don't have a nice curvy linear relationship, or even a quadratic relationship, when our relationship between data is very haphazard, very messed up, very complex relationships, then it is very useful. Decision trees can actually be more accurate than regression. And also, the other beauty of decision trees is it's explainable as well. It's actually I've just explained to you very simply, the decision tree that is used to predict who survived in Titanic. The other thing is decision tree can also be used for regression, like not only just binary prediction of 0, 1, or actually multiple predictions, 0, 1, 2, 3 as well, or 0, 1, 2, 3, 4. Many groups can be predicted using decision trees. And it can also work as predicting an amount spent, predicting chance of someone, so predicting like, how much a discount would work, how much someone's gonna spend or invest. So all these numeric predictions can be done with decision trees as well. It's simple, yet it's quite accurate most of the time. And it can model very complex relationships very easy. Not suitable for linear or curvilinear relationships, because if the relationship is simple, then regression is more accurate than decision trees. Decision trees are more accurate in complex relationships. So here again, decision trees can also be used to predict fraud and defaults, or prediction of customer churn, and all these things. It's basically the same, like regression and decision tree can be used in very similar situations, depends on how complex the data relationship is. And that's why this is another very important thing about supervised machine learning models, is there is no one answer. Sometimes you need to try out different models and then identify the model which fits, like has the best accuracy. Because as I say, supervised model, the beauty of supervised model is it gives you a prediction of accuracy. So you can, like when we work with supervised model, we normally don't stick to one. We actually apply all the supervised model in a situation and identify the model which is the most accurate for my case. And to be honest, there is no golden rule. There are some suggestions like these I'm putting in here, but there is no golden rule that, this model will be best for this model will be best for that. Neural networks. And I call it a black box because neural networks are a very complex set of calculations and not a single calculation. It's a set of calculations. If you look at the diagram in the left, it takes in, so this neural network takes in two inputs. So two variables from the data set. Then it transforms these variables into different hidden layers. There is just one hidden layer here. A neural network can have 10 to 15 hidden layers where these variables are transformed in different ways to reach the output layer where the prediction is. So the prediction could be whether someone's defaulting or not, or the prediction could be how much someone's going to spend in my website, or the prediction would be, is someone's going to be a customer in my website, a yes or no prediction. It will go through multiple layers of model fitting, multiple layers of calculation, and then reach this place. And it's also very mathematically heavy. Now, it's very good. And I mean, it's super powerful for accuracy. If prediction accuracy is very important to you, not about understanding what the model is doing, or which factors contribute to your output. All you care is the output. All you care is your prediction and nothing else. Then neural networks come in handy. But a neural network, to train a good neural network, you need a considerably large data set, much bigger data set than a regression data set or a decision tree data set. And very good at any complex relationship. Even simple relationships, it's more accurate than regression, or it's more accurate than trees. But it's not suitable if you are trying to understand, not only you're trying to predict, but also trying to figure out which factors matter, which factors play the major role in this person defaulting. That answer will not come from neural network because it's a black box. And well, normally neural networks, common uses are natural language processing, where it tries to process a language, like, process a text and understand what the language of the text is, what the sentiment of the text is, and group words together to make some meaning out of it. So natural language processing, neural network has been a God-gifted thing. The other thing is about automated vehicles, where these vehicles navigate themselves using the visual or the sensor data they get. In both these examples, if you think about it, these processors don't really care about what is the process itself, which variables contributed and which did not. It only cares about getting accuracy, understanding the right language, right sentiment, making the car take the right turns. So these are all about, the outcome, which is as accurate as possible. That's when neural networks come in. So I didn't want to put too much because, I mean, we are limited by 1 hour. But the suggestion I made was basically the concept of ensemble learning. So ensemble learning can have, like, mostly it's common about 3 types of models. So one is called bagging, another is stacking, another is random forest. So bagging, the full form is bootstrap aggregation, and we won't have enough time to cover that, and we can actually discuss it even in the next session. But more importantly, let's discuss about stacking and random forest quickly. Random forest is where instead of growing a single tree, what random forest does, it grows multiple trees. This is a single tree. So instead of growing one tree, it decides to pick different variables each time and goes through an iteration to build a different tree. And not only picks different variables, it also picks different chunks of the data set. Why does it do that? Because a random forest tries to figure out many various, builds many various trees out of small chunks of the data set to come up with the most ideal collection of trees called a forest to make a very accurate prediction. That's what random forest is. On the other hand, stacking is the one that I suggested, Kashyapu, where stacking is about, it actually begs the question that why one type of analysis? We can do regression, we can do binary regression, we can do neural networks, we can do bagging, we can do random forest, we can do decision trees. So why limit us to just one? Because in the end, as I say, there is no one single machine learning model that is optimum for a certain situation. So what it does, ensemble learning, specifically stacking, does is let's use all the tools together. Let's fit a regression model, find out the accuracy of the regression model. Let's fit a binary regression model. Let's find out the accuracy of the binary regression model. Let's fit a tree. Let's find out the accuracy of the tree. Let's fit a random forest. Let's figure out the accuracy of the random forest. Let's fit a neural network and find out the accuracy of the neural network. Then, since we have the accuracies, then there are 2 things that we can do from there. A simple thing is we have 6 models here. I mentioned just 6 models here, and we can average the prediction of the 6 models to figure out what is my prediction. It's kind of like the wisdom of the crowds, where the wisdom of the crowds is wisdom of the crowds. Here is wisdom of the models together. The other is we also know the accuracy of each of the models, right? So since we know the accuracy of each of the models, we create weights based on accuracy. The model which is given the highest accuracy will get higher weights. The model which gets lower accuracy gets the lower weights. And then using this weights, we create a weighted average prediction. Now, why not just use the most accurate model? Because a model is trained on past data. What is the guarantee that the past data, like the future data, is going to be as good as the past data, or as nice, or as good in relationship to the past data? There is no guarantee. So when we are using an ensemble of models, stacking of different models, and then based on the accuracy of these models, we are voting. That is, calculating a weighted average. We're calculating weights, where high weights are for high accurate models, low weights are for low accurate models. So we create a set of weights and then use that weights to make a weighted prediction of the future.